I'm gonna ask the.
There is noise. We can
Okay.
check it.
Yeah. So good morning, everyone. Let's get the seminar started. Today we have Rafael Fernandes, who is a professor at the University of Minnesota and is now moving to Urbana-Champaign this coming fall. Rafael, well, is very well known in the community of strongly correlated systems. He worked a lot on iron-based superconductor, and he's an expert in nematicity. So today he'll talk about altermagnets, and yeah, the floor is yours.
Thanks, Maria. Thanks for the invitation to be here. As I was telling Maria, it's my first time here and actually in Spain, so it's very nice to be here. I want to tell you a bit about altermagnets. It's a relatively new idea that has been proposed and has been gaining a lot of steam. So please interrupt me at any time with questions, okay? If I don't get to the end of it, that's fine, as long as everybody had a good time. All right, so actually I'm going to talk mostly about this first work here, but I'll also touch on other things. So these are my collaborators. Turan Viral, my colleague at Minnesota, Rodrigo Carvalho and Rodrigo Pereira in Brazil. We worked on this first thing. That's going to be the focus of my talk. With Georg Schmalian and my student Ansra Kaborti and Georg's student Charlie, we've been working on piezomagnetic properties. And with Jorn Vanderbos and Dania Antonenko, we talked about some additional topological properties, which is also part of what I'm going to discuss today. All right, so let me start by giving a brief overview of altermagnets. And Maria knows that because she was in my group a long time ago. I always say to my students and postdocs, always use figures, right? Don't do too many equations. And so my students, when I was giving one of these talks, they decided to say, oh, what is a figure to represent altermagnetism? And so I want you to tell me what you think it is. And they asked ChatGPT, and that's what it produced. It makes me uneasy. You know, maybe the day Skynet dominates, we work in altermagnets are going to be considered evil. But for now, I don't think that this represents altermagnets. So let me start by giving you a very straightforward or a very precise definition of what it is. So let's consider spins. And for now, I'm going to turn off spin up top. So I only have spin up or down. I don't care which direction it points. And the question I ask is, what kind of symmetry operations in my crystal I can do that undo time reversal? In other words, when I combine time reversal with a different symmetry, that leaves my system invariant, okay? So if I have a ferromagnet, time reversal brings the spin up to spin down. And obviously, there's nothing I can do that will bring me back here. So I break time reversal, and that's it. Okay? And the main consequence of that is that I'm going to get spin split bands. Okay? So if I combine inversion, which is I here in time reversal, that means that spin up and spin down bands are degenerate. That's what usually happens. But here in the ferromagnet, I break time reversal, so spin up and spin down bands are no longer equivalent. And because of that, I'm going to open a gap or a split. It's not necessarily a gap. And I'm going to refer to the splitting as spin splitting or Zeeman splitting. They're all the same thing here for me. There's no magnetic field. And this splitting is usually uniform around the Fermi surface. Let's go now to the other case of an antiferromagnet. Now I have spin up and down in a staggered way. I can apply time reversal. So I flip blue and red. And I ask, can I come back to where I started by just doing a crystal, symmetry of the crystal operation? And the answer is yes. If I combine time reversal with a translation shown here, and this is a translation of the non-magnetic in itself, I get back to where I started. Okay? So this operation usually goes by the name P prime. It's just time reversal and translation. And that is enough to actually ensure that the bands are spin up and spin down remain degenerate because translation doesn't do anything to K. Okay? And in this case, again, I have no Zeeman splitting or no spin splitting of the bands. That's a very well-known result for collinear antiferromagnets. Now let's do a little let's change a little bit my lattice. Let's say that for some reason, think of ligand atoms, right? Or like cages or octahedral or tetrahedral. These two atoms, they actually experience different environments locally. So I'm representing this by these losangs here. Okay, so I have two different orientations that are related by a 9-degree rotation. So now in this case, you see my unit cell enhances, is bigger, and it has actually now two atoms per unit cell. Okay, and now I do what I same kind of magnetic border that gave me antiferromagnetism. Right. So in other words, I put spin up and down in a staggered fashion. Now you see that because of these ligand fields, I do not change the size of my unit cell when I have magnetism. So it's a Q equals 0 order. So I can no longer use translation to quote unquote undo time reversal, right? But there's another thing I can do, right? So if I apply time reversal and I follow it by a 9-degree rotation, I get back to where I started. So this is precisely what is an altermagnet, okay? What is an altermagnet? Altermagnet is invariant under time reversal followed by rotation. The rotation here being very general, okay? It could be just a straightforward rotation as I'm showing here. It can be a proper rotation. It can be a non-symmetric operation as I'll show later. But anything that involves a rotation gives me an altermagnet. And you see what this implies, right? Again, I don't have spin orbit coupling. Now, because of my rotation, spin up and spin down are related as long as I apply this rotation on my momentum. But the other way, so generally, K and the rotation of Ks are different. So I'm going to get the spin splitting, even though I have no spin orbit coupling, even though I don't have a magnetization. But there are some directions that are invariant in the rotation. And that will give me nodes. So generically, what I'm going to find is that my magnetization will be modulated. So you could think of this as a D-wave ferromagnet. The name can be helpful or also not helpful, depends on your point of view, because it's not really a ferromagnet. There's no magnetization. But the D-wave here is just to remind you that the spin splitting has a D-wave form factor. Okay? So this example that I'm showing here is a D-wave ferromagnet, but it could be G-wave, I-wave, any, even in momentum. Okay? And I didn't mention that, but this idea was very nicely articulated and proposed in this paper by Lieber Smiko, Iris Sinova, and Thomas, explaining the symmetry operations here. Now, this is one example of something that people have been interested, which goes by the name no relativistic spin splitting, which is the idea that I can have spin splitting of the bands even if I don't have spin orbit coupling. That's why this name no relativistic. And for example, and again, I'm just showing you some papers that have been discussing this idea. I think one of the most known examples is manganese fluoride, which is a rotary structure, which I think most people would have called an antiferromagnet, but now we understand it's this altermagnetic here, okay? Now, again, so this gives me these three different classes. And again, these are two papers in PRX that I strongly recommended by Lieber, Heidel, and Thomas. So you can think of how the symmetries that leave the system invariantly combined with time reversal and the splitting of the spin up and spin down bands. Okay? If there's no symmetry, there's a uniform splitting, this is the ferromagnet. If the symmetries are either translation or inversion, like for example, if you have Niel order or staggered order in a honeycomb lattice, that is Q equals 0, but it's related by inversion. Then this gives no splitting, and this is an antiferromagnet. And altermagnet is when you have combined with time reversal a proper or an improper rotation, and then you get a modulated splitting, so on average is 0, but it has nodes and it's even in momentum. Okay. Now you can say how robust or how formal this classification is, and this is actually what was shown in this PRX. It's actually very formal and very nicely expressed in terms of spin groups. If you're not familiar with this term, it's different than magnetic groups. So magnetic space groups, in those, you assume there is spin orbit coupling, so your spins will rotate when you rotate your lattice as well. Spin groups, which is something developed a while back, you consider the rotations in spin space separately than rotations in momentum space or in real space, and that's why you have these kind of symbols here. And in this paper, was shown there are 3 types of spin groups, and for each type, you associate one kind of magnetism. So type 1 is ferro, type 2 is antiferro, type 3 is altermagnetic, and you can remember, if you have magnetic groups, you have also 4 types, but this is a little bit different here, okay? So you can make this in a formal group theoretical way, right? Now, what I'm going to be exploring this talk is what happens when you turn on spin orbit coupling. And it's important to notice and say right away that you don't lose altermagnetism the moment you turn on spin orbit coupling. But there are some additional things that happen. What is the example? So I think the most studied example is the rutiles, so ruthenium oxide, manganese difluoride, copper difluoride. Because in this case, you remember those lozengs that I drew? Well, they also exist here. It's a little more complicated because they're not in the same plane as I'm showing here, but they make the two ruthenium atoms feel different environments. So if you have spin up and spin down, they're not related by inversion or translation. They're related by actually a non-symmetric operation that you can think of rotation. And if you do first principles, then, if you do first principles, turning off spin orbit coupling is actually easy. You don't need to turn off anything. You just don't turn it on. And you can actually see that you get huge splitting. So this is ruthenium oxide, this is red and blue, and there is a big splitting here of order of EV, which you'd never get if you had just spin orbit coupling. I'll later show a microscopic model that allows you to get an intuitive understanding, or at least some understanding of why this splitting is so large. This splitting doesn't come from spin orbit coupling, it comes from hopping, and that's why it can be so large. Since then, many materials have been proposed as altermagnets, and again, some of them people in the past may have identified as an altermagnet, but now you can put in this classification. This is a very nice paper that lists a lot of materials and the size of the spin splitting. And you see there's a common theme here, which I'm just going to tell you because it's hard to see, but it's usually here. See chromium, manganese, iron, cobalt. It's usually a, let's call magnetic element, if you wish, surrounded by some different local environment, okay? Experiments. If you've been following it, you know there is a controversy, which is ruthenium oxide an altermagnet? The real question is ruthenium oxide magnetic or not? So manganese difluoride, there's no question. The ruthenium oxide is a bit different. I'm just going to tell you what has been discussed here. These papers are very recent. This paper here, so this goes back their early scattering experiments a few years ago, where they saw magnetic moment in ruthenium oxide. There have been, there's a very recent paper here by this group saying that they don't see anything. This is mu-SR. They also do neutron scattering. Now, this is a paper from my collaborators in Minnesota, a group of Baraj Alan. They can grow extremely thin films, 2 nanometers thick, okay? And there, you can do second harmonic generation. Second harmonic generation is great for you to try to extract a magnetic point group, and you can see there's a clear hint at a certain temperature, and the best fitting here is to a magnetic point group that is what you expect for an altermagnet. So films, bulk, thick films, thin films, there are lots of questions going on, which makes it exciting. Okay, and if everybody agreed, maybe it would not be so exciting. There's also very recent and very nice data of ARPIS. Here are 2 other candidates, manganese telluride. I'm going to call this chromium and timonide. I'm not sure that's the real name, but I'm a theorist, so I can get away with calling things what they may be. But anyway, so manganese telluride is a very nice Nature paper here, where they see, again, this is not spin result ARPIS, but you can see the splittings and you see the modulation in the splittings, right? If you see a splitting, that's very clear. This splitting is modulated according to what you expect with altermagnet. Last week, there were 3 papers appeared doing ARPAs in chromium timonide, which is another hexagonal or system with 6-fold rotational symmetry. And they see here splitting again, that is consistent with what you expect. And I saw just, I think last Friday, there was another paper that does a spin resolved ARPAs claiming something similar. So it's very active, lots of things happening. Why theorists are interested? Well, it's not very hard to entertain theories, but let's say there are several different directions people are interested. I think one of the first ones was for spintronics. I'm not an expert, but you can see why this would be interesting. For example, if I inject a current along the direction that I have spin splitting, I'll get a spin current. If I inject it along a direction that has a node, I'll not get a spin current. So it has been proposed, actually, the first paper by Lieber and Hayo, that these materials has interesting properties that make it ideal for spintronics, okay? It doesn't have a net magnetization, so it is not perturbed by magnetic fields, but at the same time has very fast collective modes. People have also been interested in interfacing with superconductors because, well, why not? I work on superconductivity, and if you ever tell me I found a new state, I'm going to try to stick a superconductor in it to see what happens, right? And here, there's a very nice, you can think of this analogy, right? People have talked about interfacing ferromagnets and superconductors. Now think about a ferromagnet interfacing with a D-wave superconductor. This would be more or less, if you think in a very loose way, of interfacing a D-wave ferromagnet, which is an altermagnet, with an S-wave superconductor. So you can see opportunities appearing here, and there are lots of papers. I'm not sure all these references are up to date, that you can, by doing these interfaces, you can realize finite momentum theory, topological superconductivity, Majorana modes, you name it. And the other thing that is interesting for potential applications is something we've been playing with, but I'm not going to talk here in the seminar more, is piezomagnetism. So piezomagnetism is different than magnetostriction, which is a generic property of magnetic materials that if you apply a field, you see lattice distortions. Here, piezomagnetism, which was, I think, one of the first discussions in this paper by Dzialujinsky, if you apply a magnetic field, you get a distortion that is linear in the field. For instance, this is a simple example for an altermagnet. If I apply a field out of the plane, I get a shear distortion in the plane in one direction. I flip the field, I flip the distortion. Okay, so this would be piezomagnetism. And when people ask me what is the order parameter of an altermagnet, we can give, if I want to give an experimental motivated question, I'll say that for the vast majority of them would be a piezomagnetic property. Okay, and there are lots of interesting effects. It provides a very nice way of realizing random fieldizing model, but with a controlled random field, because the random field has to couple, you can turn on and off with external field. And it also has a very non-trivial coupling with phonons. There's a hybridization, which is a generalization of the idea of a magnet polar in regular magnets. Okay. All right. Any questions? Okay. So I want to talk here today is about what happens when I turn off spin orbit coupling. And I will show that we went down the system with some interesting topological properties. Before going that, however, I want to make a point how this altermagnet connects to various ideas in correlated electron systems that have been going on around. Okay, so let me start by trying to make this connection. Again, this is mostly trying to organize some thoughts and how this idea that has been coming more from a more weakly correlated perspective applies to strongly correlated systems. Okay, so this is more or less a strategy that I have pointed out where how people have been looking for altermagnets, right? You got a magnetic atom, right? Something that has manganese, iron, cobalt, nickel, and then you see local environment changing and look for altermagnetism. I wanted to know the other question is, can I get this in the strongly correlated systems where electron-electron interactions are playing a more significant role? Oops. So the first one, which I guess I erased the slide, would be to look for Mott insulators. Because Mott insulators, well, they are, for the most part, magnetic. And it turns out that there is a certain class of Mott insulators that are natural candidates for altermagnetism. So these are some perovskites that are, or I'm going to be talking about these perovskites. And a lot of them are Mott insulators with this Neal type antiferromagnetic order, right? So this is just a picture of an ideal perovskite structure where you have the oxygen octahedral, and inside you're going to have, either copper, manganese, titanium, ruthenium, vanadium. And these have been studied for lots of different reasons. They have in common that all of them in some regime are Mott insulators. Okay, and here's just a projection of the plane showing this octahedron. Okay, all right. So this is an EL type antiferromagnet, also called G type order. We understand this well. But perovskites, because of this, depending on the size of the atoms involved, they're actually going to acquire these octahedral rotations. There are lots of different patterns that can appear, but in a large number of them, it gives you an orthorhombic group called PNMA, which lowers the symmetry. Okay, it actually, what it does is that it makes the unit cell larger. So as you can see here, now, if I want to draw a new unit cell, I need to actually enlarge my unit cell to get to account for this octahedral rotation. This sounds a lot like what we discussed before, where you have a magnetic atom in a different environment. The difference here is that the magnetism is coming from a Mott insulated state. And in a lot of the perovskites, you can, to some extent, control the size of these octahedral distortions, either by the size of your, for example, in the rare earth titanate, the size of your rare earth, by applying pressure or by applying strain. So that offers an interesting possibility here, okay? So let's just go over and show you that this is indeed an altermagnet, right? So this is the ideal perovskite structure. The paramagnetic in itself is different than the magnetic one. So I'm showing this again, a projection to make life easier. The moment I have octahedral rotations now, as you can see now, my unit cell has now, at least in this plane, the projection, double the size, and it matches precisely the magnetic unit cell. So this is a good candidate for altermagnet. So let's see what operations I need to do to relate to compensate for time reversal. All right, so, okay, so this is my initial system with the octahedral rotations. Now I'm showing you here the unit cell so we don't get lost. So I do time reversal. Time reversal again, just changes spin up and spin down, okay? Blue and red. Now what do I need to do to get back to my initial configuration? Let's first do 180-degree rotation. So I drew here an axis, okay? And then all I did from here to here, you see I'm going to rotate. So this guy is going to go here, this guy is going to go up. That's all that happened, okay? All right, well, this is not enough, right? This clearly made my units are not matching, even though both have two atoms. But what I clearly can do is a half translation, right? If I do a half translation along the direction of the axis, so I screw, I actually get exactly where I started. And that's what I mentioned earlier, right? Usually, in several of these materials, the symmetries that make them equivalent involve some non-symmetric operation. Okay? So here's the screw axis, and then you get exactly where you started. Okay, so this is just showing that these PNMA structures are intrinsically altermagnetics without spin orbit coupling. So this is another place where you can look. Excuse me, and a particularly promising series of perovskites are these rare earth titanates, because here you have precisely this PNMA structure, and the size and the amount of octahedral rotation depends on the size of the rare earth. So you can control with rare earth, you can control with pressure, strain. So there's lots of tuning parameters, okay? And this is just a DFT calculation showing what happens when you start rotating with the spin density and why it's no longer just an antiferromagnet. Okay, so this is one way where you can get this multi-insulator and octahedral rotations. But what if I don't want to invoke any structural degrees of freedom? Can I still get an altermagnet? And the answer is yes. So think of a different situation. I start again with my magnetic atoms here, but now I make the environment differently, not because of a lattice distortion, but because of some orbital order. Okay? I can always have that. This case would be an antiferro orbital order, where you see, for example, here, I'm doing some atoms have xz plus yz, for example, this xz minus yz, and this is equivalent to this situation. In fact, that's a way where you can get structural distortions as well, right? And so if the key point here is that if you combine antiferro orbital order with antiferromagnetism, you can get an altermagnet. And this is actually part of a solution of a wider class of systems, and they're described by this effective model called the Kugelkowski model, where you have spins, and you also have pseudo spins describing these orbital degrees of freedom. Okay, and if both of them are oriented in an anti-ferro kind of way, what I mean is both want to be anti-ferromagnetic and anti-ferro orbital order, which means that the scale here generally has to be negative, you would get something like that. Okay? There's another way yet, which is to think of altermagnetism in terms of multipolar moments. What do I mean by that? Let's go back to classical physics, say that I have a dipole moment, and I write down the terms in a multipolar expansion. Well, the leading order term is always, of course, a dipole. If I want to go to the configuration of moments that don't have dipole moment, but have a quadrupole, all I need is to put two moments that are related by inversion. Remember, under inversion, the moments don't flip. So this breaks inversion and time reversal. Or I can also, if I want something that doesn't have quadrupole, the next order is octopole. This is a distribution of 4 dipole moments. You see now that there is up, down, up, down. And when I draw these pictures, you can immediately recognize kind of magnetic orders inside the unit cell, right? A ferromagnet, an antiferromagnet here, is just a Q equals 0 order related by inversion. And this is the altermagnet, where the up and down are related by rotation instead of inversion. Okay? So what I'm trying to say is that you can think of whenever I condense a multipolar magnetic order parameter, I will get an altermagnet, provided that is an even parity. Okay? And this point has been made. This is this paper by Nicole Spalding, Libor, and us. We mentioned this idea here. Just to make a point very clear, I'm not saying that altermagnets are equivalent to a magnetic octopole moment. Saying that a magnetic octopole moment is one example of an altermagnet. You can have other kinds of terms, in particular toroidal terms, but I'm not going to talk about it. Okay? But that actually offers another way for you to look at altermagnets. Look for it. Do I have systems that have magnetic multipolar order? And again, multi-insulators are actually good for that. It has been studied for a while, and I'm showing here 2 different examples. When I have strong correlations and strong spin-orbit coupling, if my ground state is what's called no-Kramers doublet, so you need to do L, right? You have L and S, so you need to go to a spin J. And in some cases, this state is twofold degenerate by no Kramers. It means that the degeneracy is not because of a pseudospin. And in several of these cases, what this pseudospin corresponds to is a multipole moment. I'll give you an example here. So these are 2 different examples. One is this double perovskites, which have osmium, which has a large spin-orbit coupling. This is actually a metal, but because of the praseodymium here, you also get this state. So let me just walk you through that. You start with praseodymium 3+, plus spin 1, L equals 5. In the presence of spin coupling, you get a J equals 4, which has a line-fold degeneracy. Now you put in the crystal, it splits into these levels. And the ground state here is a non-parameter doublet. What it means is that in this case here is a cubic system. It belongs to two-dimensional reduced representation. So you can describe a pseudo-spin. Again, I need an atomic limit, in the limit of very large U, okay, to explain that. So the pseudo-spin here, again, up and down are no longer spin up and spin down. It's not ferromagnet, it's not magnetism. But it turns out that tau Z, which you would associate with spin up and down, is actually the product of these three J's, which is an octopole. Okay? So people have discussed in the past, especially heavy Fermi compounds, this idea of multipolar moments. And you can think of them in real space as, again, the realization of altermagnets. Okay, so this is another way of getting them. You can do the other way around. So I started the strong coupling limit, and I get this from the weak coupling limit without requiring any local, any structural degrees of freedom. Okay? And there is actually an answer here too, which has been studied quite a bit. I talked to you about multipoles, and the multipoles I talked to you about were defined in real space, right? Because this is appropriate to think of insulators with strong U. There's nothing that prevents me from defining a multipole in momentum space. Right? In momentum space, I have a spin distribution, and I can also expand in spherical harmonics. Okay? So the same way that I can have these multiple moments in real space, I can think of these multiple moments in momentum space, and this is precisely that idea of a D-wave ferromagnet, if you wish. The form factor here is even in momentum and goes to zero when the momentum goes to zero. That would be an altermagnet. So the question is, do I know of systems that are unstable towards these kind of magnetic orders? And the answer is yes. It actually goes back to Pomerantjuk. In the 50s, Pomerantjuk studied what is now we call Pomerantjuk instabilities, which is essentially a generalization of Stoner criterion for ferromagnetism. So what Pomerantjuk studied was take a Fermi liquid, okay, which has its excitations, which are the dressed electrons, and these interactions, you can now write interaction between these quasi-particles, okay, and you can expand these spherical harmonics, and you get interactions that I usually go by the name or by the notation FL. These are just called, so sometimes lambda parameters. So L here is the angular momentum. S and P means whether it's in the triplet or single channel. And what Pomerantjuk showed is that when this interaction is large enough, negative in this notation, so density of states times this interaction smaller than this value, the system is unstable towards instability on that particular angular momentum channel. Again, if you do L equals 1, okay, sorry, L equals 0 and triplet, you get precise Stoner criterion. So this is a Stoner criterion for higher angular momentum. What do they mean in practice? Actually, they're very known. We look at them all the time. In the charge sector, meaning I don't have any spin polarization, a single channel, L equals 0 is really not active in the sense that I have Luttinger theorem, so I cannot really change the size of the Fermi surface. L equals 1 would be something that, well, Maria looked a lot at it, which is what we call the ferroelectric metal, polar matter, right? Metals that break inversion symmetry. So this would have a dipole moment. And L equals 2 is something that I worked a lot, and this is pointed out in this very nice paper by Steve Kivelson and Eduardo Franchi and Vadinho Ganessian. It's nothing but a charge for the polar order, which is exactly enigmatic. Okay? I took these figures from this very nice paper by Hayami. Now, if you do the same in the spin sector, L equals 0, again, there's the L here is a little different than what you define different ways, but it gets a ferromagnetism. L equals 1 would be loop currents or P-wave magnets. And L equals 2 gives precisely nodal points in the spin splitting. That is the altermagnet. Okay? This paper actually was very extensively studied in this paper by Kai Sun, Eduardo Fradkin, and Shuzhen Zhang, and they call this nematic spin nematic. I talked to Eduardo, why do you guys call that? Anyway, they call it nematic spin nematic, and it actually has very interesting collective excitations, but it is an example of an altermagnet. Okay? So that's what I mentioned. It's precisely the same wave splitting here. So from a weak coupling perspective, any even parity spin triplet for magnetic instability will be an altermagnetic matter. And there's this nice paper early on by Kunis where they make this point as well. And this closes this loop where what I wanted to make connections between different problems or problems that people have been interested to show, altermagnets provide a nice framework to describe these connections here, right? How you, besides the usual way, you can also get from multi-insulators or from strong correlations or weak correlations, even without, even if I were to turn off structural degrees of freedom. Okay. And this is the picture that I wanted to summarize this part of the talk, which is I can go from metals to insulators, increase interactions, and identify different phenomena, magnetic instabilities, multipolar magnetism, orbital order, how they all give rise to things that are within altermagnetism. And here is just showing that there's a connection with unconventional superconductivity in the sense that I can define superconductors that are S wave, D wave, P wave. I can also define altermagnetism as D wave, G wave, or I wave. Magnets. Okay. Any questions before I continue? How much time do I have? 1 hour, thanks.
About, let's say, 12 minutes.
12? Okay. So in the next half an hour, no, it's okay. Again, as I said, even if I don't get to the end, that's perfectly fine. Now I want to tell you what happens to all of this nice stuff when I turn on spin orbit coupling. Even if it's weak, it's there. So it will be important to understand, right? And as you know, the moment I turn on spin orbit coupling, when I make rotations in real space, I need to rotate the spin. So this is a 180-degree rotation axis. If the spins are perpendicular to the axis, they rotate when I rotate the lattice, but if it's parallel, they don't. So they are no longer independent. We know that in a ferromagnet, what happens when I turn on spin orbit coupling? It chooses a direction. What does it do to an altermagnet? So as I mentioned to you, right, this is a very nice table in the paper by Lieber. Without spin orbit coupling, I can write down my spin, momentum-dependent spin as a magnetization times form factor, that it would be D wave or not. It turns out that the moment you turn on spin orbit coupling, this description is incomplete. What we found in this paper is that each component of this, you no longer have one spin quantization axis, but each component of the spin will have its own modulation. So in other words, altermagnets, when you turn on spin orbit coupling, become intrinsically non-collinear, if you want to call it like that. Okay? So let's see why this happens and what are the consequences. Again, this doesn't mean that there's no altermagnet, just change the sum of the properties. Okay, let me take an example which is being used to describe the root tiles. So I have a magnetization, and my D wave form factor here is just kx times ky. Okay? Very good. So without spin orbit coupling, the spin transforms as the reduced representations of SO3 or SO2. Right? But the moment I turn on spin orbit coupling, different components have different transformation properties. So sigma z goes as A to G. By the way, these are tetragonal systems, so I'm just doing D for H. X and Y goes as EG. Okay? So let's see what happens, right? So before I had B1, this is a B2G, and this here is just the vector representation. Now that I turn on spin orbit coupling, this becomes, let's make the moments point along Z. Now you see, this is A to G, this is B to D, so I get B1G. Time reversal odd, of course. Great. But I can construct another combination of spins along X and Y that also transform as B1. This one here, KYZ sigma X, KZ, KX, sigma Y. Well, as we know, if two things have the same irreducible representation, they have to appear together, right? So what it means is that I shouldn't really, the moment I turn on spin coupling, now I chose my moments out of the plane, what happens is that the in-plane moments are also going to acquire modulation. Notice that they have different B waveform factors, but if I look in the plane, k is equal 0, this guy is gone, and I get something that has just sigma z, okay? And the zeta here is just the anisotrope, okay? Very good. So that was the point that I was trying to say, that the moment you turn on spin coupling, they gave an example, this is going to happen always, okay? So these allow us to write a very simple low energy model for altermagnets, which is my order parameter times d dot sigma, right? Because I can just write, so I go back here, oops, I can write my d vector, I can write this d as a vector as well, okay? So I can think like this, and the moment I diagonalize the Hamiltonian, and here I'm just taking a very boring spherical Fermi surface, you see that it's not collinear, right? If I plot the eigenvalue projected on the sigma z, as I start moving away from kz equals 0, I start mixing with other magnetic moments, okay? And the other nice thing that you see in this picture here is that there are some of these points that are the pinch points, is where the vector d is 0, okay? Now, if you don't believe me, if you want to see this from first principle, here's very nice DFT calculation on ruthenium oxide, not at k is equal 0, with spin coupling, and you see that you do get moments that are not sigma z. If you're still not happy with that and you want to see real space, there's actually a very nice way, which is to look at their Wyckoff positions. So, manganese difluoride, you can look at the magnetic Wyckoff positions, and initially you say that I'm wrong. Say, oh, wait, I look at the Wyckoff positions of manganese and fluoride, and I clearly see here that the moment can only point along Z. Where is this non-collinear moment? Well, there is another Wyckoff position in this structure that in the case of these rutiles is actually empty. We go here, X. And in these positions, you see, I cannot have moment only along Z. In fact, if you draw the moments, you have this autopolar structure I told you about, right? So this is where it is now. Remember, these are not systems in the atomic equilibrium. Even if I have magnetism coming from manganese, the spin density is not restricted to that atom. So that's exactly what I'm saying. Okay. All right. What does it do? So, and here's now the other side of it. I chose my moment to be out of the plane. What happens if I chose in the plane? Well, in this case, it transforms as the EG reduced representation, but that's exactly what a ferromagnetic moment is. So you see in this case here, if the moments point in the plane, I'm going to induce weak ferromagnetism. So in this case here, out of plane spins is a pure altermagnet, in plane spins mixed with ferromagnet. Now, it depends on how you want to see that. What is interesting in this case is because I have ferromagnet, I'm going to be able to see manifestations of this, indirect manifestations of this altermagnetic order parameter in quantities that only exist if I have a magnetic moment, such as Hall effect, anomalous Hall and Kerr effect. So altermagnets, pure altermagnets do not have anomalous Hall or Kerr, but if the direction of the moments induce a mixture of ferromagnets, that they are realized. Okay? And you can now play this game and you classify for the most standard groups that you can have. And this is just to show you that we actually did something. But you see some of the components, they have D wave, but these other ones have G wave, for example. So we start mixing things. But let me tell you, I'm going to skip this just to say that this form here suggests a connection not to D wave magnets, but to triplet superconductors, but to triplet superconductors we can talk more about it later if you're interested. It's just an analogy anyway. But I want to tell you like a concrete manifestation of this, which is what happens to the nodal directions. So let's take the case without spin orbit coupling, right? Spin up and spin down is proportional to that d, which here is a scalar, kx, ky. So it vanishes along these two planes. There's a lot of zeros. The moment I turn off spin orbit coupling, I'm only going to get zeros if the whole vector, the magnitude of the vector is zero. This seems over-constrained, but it's not. As you can see, I can make the three components being zero out of these three lines. Where kx equals 0 and ky equals 0, for example. So what you see is that these planes here, they now reduce to lines. And this happens for almost all altermagnets that, we looked, we have all of these. Now, here's the interesting property. Now that I'm allowing the spin to see the lattice, you see that all these lines, they're always residing on the mirror plane of the lattice. So it turns out that these lines, they're actually crystalline symmetry protected nodal lines. They're protected by this mirror symmetry. And this, again, this is one example, but we saw that in every case that we looked. What does it mean? It actually gives an extra stability for the altermagnetic phase. Let's say that I apply a magnetic field. Okay? So now if you say apply a magnetic field, all these nodal lines should go away because I should get a Zeeman splitting, and the Zeeman splitting should just essentially remove all the genesis. What is very nice is that in this formulation, in terms of the d vector, you can interpret a magnetic field as a shift of this d vector. And it's true that if I apply a field along an arbitrary direction, not a particularly high symmetry direction, I gap out all these nodes. So for example, here, I apply 45 degrees in the plane, and if you try to find where d tilde is 0, you can quickly convince yourself there's no solution to these three equations. But if I apply the magnetic field along a direction, that is perpendicular to one of the mirror planes, so in other words, I'm keeping a mirror as a symmetry, that the lines, the nodal lines on that mirror cannot be immediately gapped. So it means that I have a much more stable altermagnetism here. So for example, if I apply the field along z-axis, I can still solve these equations by having ky and kx, sorry, by having kz equals 0. Right? So what happens in this case? Well, the only way that you actually kill these lines is if I keep increasing the field. It's not a small field anymore. And here's a picture in the lattice, in the Brillouin zone. These are the nodal lines. They form these squares. The moment I apply a field, you see I only get 2 of them that remain, and they form these loops. And all I can do is have these loops collapse. And when they collapse into a point, that's finally when I lift all the gaps. This is nothing but a topological transition, where I have to eliminate or kill completely the nodal lines, okay? So I think this is the main thing I wanted to point out, is that when I go for an altermagnet, which has nodal lines, to a ferromagnet in the sense that I don't have nodal lines, this transition is, if I apply the field perpendicular to one of the mirrors, a topological transition. In an arbitrary direction, you immediately get a ferromagnet. Okay. All right. Do I have 5 minutes just to go over the?
Yes.
Okay. So I want to talk a little bit about these Chern bands and bio-nodal lines. Oops. Okay. So far we've been only talking about symmetry. We wanted to do symmetry, but also think of a microscopic model. And how do I describe a model that has altermagnetism? So one of the simplest models, which actually was also discussed in this paper here by Brecky, I think, et al., is that think of the Lib lattice. The Lib lattice is a 2D lattice that has, I'm showing here, 2 different sublattices. So it says two atoms per unit cell, which are here blue and red. But they have these black squares here. They are the non-magnetic atoms in this model. Okay? This is if you think of a copper oxygen 2 layer, that's exactly what it is, right? The oxygens are this, and the coppers are here, okay? But you see that, and now I put, I can have spin up and spin down, but you see I also have two sublattices that I call A and B, right? So this here, if I have a ferromagnetic order, is an altermagnet because, again, my unit cell doesn't change, and I have to connect spin up and spin down by rotation, okay? So in this lead lattice here, I can write down my Hamiltonian, which has the non-interacting part of the electrons. And then, so I'm assuming, let's just do a simple condor-like model where I put the staggered magnetization, this N, coupling to the electrons that are hopping around. Okay? So this is the simplest model you can think. And the key quantity here is this hopping anisotropy. You see, the second nearest neighbors involving this sublattice along this direction here is different along this direction because here I don't see my non-magnetic atom. Okay, and this gives rise to this term here. So we wrote down this in sublattice space and spin space. Okay, now you can look at the band structure here, right? And here's what you find. You say, okay, well, I see splitting of order J between two copies of the bands, and these are the nodal lines. Okay, this is M gamma. So the nodal lines here are along the diagonals, and I see here red and blue are precisely the two spins. Great. So this is what I expected from an altermagnet. But then you notice, and by the way, this is a spin splitting. You see, that's what I mentioned earlier. It's proportional to the hopping. So that's why it's large. Okay? Now, what we notice that there's some additional crossings here. Oops. Yeah. These are crossing between spins of the same, bands of the same spin, but the plus and minus here are just different sublattices. So I have crossings now, and this is not a line, this is a node, so we call this a Dirac crossing, a Dirac point, between same spin, but different sublattices. Okay. And it turns out that these nodes here are protected, and that you can actually understand them as arising from, if you start with zero magnetization and you start increasing the magnetization, they actually start from a quadratic band touching. So you start with quadratic band touching, you disturb it, you get these two Dirac crossings, and I keep increasing my magnetization. The only way to get rid of them is when they meet and are removed at the Y point. So you see, we usually focus on this regime here, where the magnetization is large enough and I have an isolated band. But a lot of the times, especially when this is not very large, which I can control with temperature, I'm going to get this additional Dirac points. Okay? And you can show that this is a quite generic property. There's no way of avoiding it. Now, this is all without spin orbit thinking. So our point is that besides the nodal Zeeman spins, different spin splitting, there's also another crossing between same spin and opposite sublattice, which is quite generic. And what is nice is that if you turn on now spin orbit coupling, okay, what happens now is that you're going to get that, and you actually, I just wanted to say that you can also control, so this is the limit where magnetization is zero. You can also start in the limit where the hopping is zero, this hopping anisotropy, and now it's the other way around, right? So large hopping anisotropy, you get the Dirac points, small hopping anisotropy, you don't. Okay? But now what happens the moment I turn on spin orbit coupling? Well, it gaps this Dirac point, and you get exactly, you get now churn bands. Okay? These churn bands are actually protected by a mirror symmetry, these horizontal mirrors now, when the moments are out of the plane. Okay? So if I have this band structure here and I place my chemical potential at zero, for example, I'm going to get a quantum spin Hall effect, a quantized quantum spin Hall effect. This is a mirror churn insulator. But importantly, this happens if the magnetization is not too large, and if the moment points out of the plane. Essentially, this spin orbit coupling term here has the same role as the Kane melee in graphene here. If the moment, however, point in-plane situation is different. So as I start increasing the size of magnetization, remember what I showed here is that I have this and then this disappear. In the same way, I go from from topological insulator with near turn or turn insulator to a trivial insulator just by changing the size of the magnetization. And as I mentioned, and just to finish, if my moments are in the plane, this is gone. I no longer have Chern bands because actually in both of these cases, I actually mix with an in-plane magnetic moment. And I get either ferromagnetic or canted ferromagnetism. Okay, I rushed a little bit because I think I already ran up over time. I hope I gave you a perspective of why altermagnets are exciting. They bring together lots of interesting concepts in correlated systems. And now they also are very fertile ground to understand or to realize non-trivial topology because they have some of these unique symmetries related to rotation. And the moment you have spin-orbit coupling, you can also get this realization of these different kinds of topological phenomena. Thank you.
Okay, so time for questions.
Thank you for the wonderful talk.
Yes.
Could you remind which specific hopping you are talking there?
Yes.
When you define, and if it's general, so generally one can say that altermagnetic spin split is proportional to some specific hopping.
Right. So it's a bit subtle, but yeah. So this is the Lib lattice, and
maybe cannot. I don't know.
Well, no, I think that's it is proportional to the hopping, but let me just tell you, let me walk you through how we construct that. And you can do the same, I didn't show here, but we have the same model for Butai where things are out of the plane. But here's all in plane, okay? So I'm writing things in terms of the sublattice. So this tau x here and tau 0, they're just, T1 is just nearest neighbor, okay? And T2 is next nearest neighbor, right? So I have tau 0, so nearest neighbors is different sublattices. That's why I have a tau x. This is a sublattice. Tau 0 is the same sublattice, okay? Now, what the key point is that I need two different, if I go along A or B or along X and Y, I have different hopping, right? So here, the second nearest neighbor hopping, I don't have anything here in the middle. But if I go in this direction here, I see this non-magnetic atom, right? So they have to be different. And this has nothing to do with magnetism. This is just the structure of the lattice, right? There's several ways you can do that. You could also just write a 3-band model, make this band, the band corresponding to this atom, large energy, integrate it out, you also get the same. But this term here has to appear. And so when I have T2A is different than T2B, I can rewrite as something that is tau 0 and tau z, okay? But the key point is that you see now that you get this D wave form factor here, cosine kx minus cosine ky, because it has to do with this anisotropy, okay? So these three parts have nothing to do with altermagnetism. They're always there, right? Now I turn on this part here. This is just a condo coupling. I'm saying, hey, I have alternating spin up and down. So I have a sigma z and also tau z, right? Because they change sign when I go to different sublattices, right? The key point is that I need both of them. So let's say that I don't have this n, obviously then, well, spin splitting is 0, right? Now, if I don't have this, I'm also gonna get 0 because this still has a symmetry with respect to sigma z tau z. So it is when I have both of them that I get this. And I think this is what I try to draw here. So this is the case with PD different than 0, n equals 0. You see, this is essentially PD, right? But it's because n is 0, I need to turn it on. Now you see, I essentially make two copies, one with spin up and one with spin down, and they move a little bit. But now you see, this is the splitting that is TD. Okay, so it was there, but it was just not realized between spin up and spin down. Now you may say, oh, but why are you calling this the spin splitting? Isn't this the spin splitting? Well, I'm calling this because this is the one that actually persists all the way. This is the one that is same sublattice or in different spins. Okay, so that's the TD. Here is the other situation when it starts with TD equals 0 and N equals 0, then again, up and down are degenerate. This is almost like an antiferromagnet. Now, there's no splitting, right? But the moment I turn on TD, then you see them getting this splitting. Okay,
Thank you.
so it comes from TD, but if J is 0, I don't get it. And that's why it can be large. That's why it doesn't need to be MEV, but it can be EV. You know, now you see another, sorry, I'm just going to mention one more thing. This anisotropy has to do with the local environments being different. If I can control it by pressure or something, then you could see that I can control the size of this TD. Thank you very much.
Thanks for the talk. I have a question about this slide that you were showing before with the tau as a sublattice. In this case, this is a poly matrix for the red and the blue, or you are considering the three sides in the unit cell with a spin 1 matrix?
No, I'm doing spin half. So I consider this, again, this is a simplification, but we consider this to be non-magnetic.
Okay.
And then, I mean, you could still consider the whole thing. But what we did for simplicity is say this is non-magnetic, and that these bands are high energy, so I can integrate them out. And then all you do is renormalize these terms. So it's like the opposite of a copper oxygen plane, because in the copper oxide, these are right, the black squares are the main actors, right? That's where you have the coppers, and these are the oxygen. Here we're doing the other limit, where the main actors are the sphere here.
So you're doing this at the lip because you remind the copper oxide?
No, I don't.
No, I was wondering if you consider some other geometry with the three sides and units and like the nice lattice.
Yeah, so
I mean, interesting frustration effect.
yeah, so we had this for the lip just because this actually, and again, in fairness, these papers here, the paper here, bracket, I think this is being published right now. They're the ones that also proposed this idea. What we did was we turned on spin coupling and so on, but this goes back to this idea. It's just that this is the simplest model that shows this physics, at least to my opinion. So this is just a toy model. But since writing the model, we realized that there are materials that realize this lip lattice in layers. And so you could see that physics actually. In the same paper, we wrote this in a way that then is more similar to this other paper here by Schiff et al., where we actually, where it's the rutile structure. And then the main difference is that you have, you know, atoms above and below. So then you cannot do it 2D, okay? But you're right, provided that I have an equal sublattice, like the dice lattice is another case. And as long as the up and down spins, sides of the up and down spins are not related by inversion, the same physics should hold. And we can do now 4 sublattices and yeah.
Thanks for the nice stuff. Going back to this mapping between this altermagnets and superconductivity.
Oh, yeah. Sure. Yeah. So when people start talking about D-wave ferromagnets, you make the immediate connection to D-wave superconductors. My point is that I think the more clear analogy is with triplet superconductors. And that's because of this D vector, right? So I argue that when you have spin orbit coupling, you should really write this as a vector of modulations dot spin, right? And then I don't have spin up and down anymore, but I do have 2 bands, which I here denote plus and minus. Just the magic of diagonalizing something that is polymatrices, right? So I still have 2 bands. And now you see the eigenvalues are just displaced by the magnitude of this vector. Now this vector here is even in momentum. If you now go to triplet superconductors, it actually looks very similar. But first, this is particle-hole, this is particle-particle. And then that's why you have the I sigma y. But this is you see that looks very similar. As a superconductor, the displacement is not just linear; it's in quadrature. Right now, like this, you also have plus and minus. And the main difference, because again, this is just because of fermionic statistics, is that the d vector actually there has to be odd in momentum. So I don't know. I feel this analogy.
So it's only on the level of Hamiltonian. There's
Yeah,
no.
yeah.
So you could have like topological phases in this triplet superconductors and so on. It doesn't go with that. You cannot have
That was just, but also I wanted to say this is work in progress, and other people have also mentioned that if you ask how altermagnetism or altermagnetic fluctuations would favor superconductivity, you're gonna see that it has to be, or most of the time it's gonna be triplet. But this was just
favor. So if there is a transition to superconductor, what do you mean favor? If there is
if I have altermagnetic fluctuations, so magnetic fluctuations, ferromagnetic favor p-wave superconductivity, and I can ask the same question, right? And you're gonna, because they break time reversal, generally they will like some triplet. But that was not the point I was trying to make here. I'm just saying that this is just an analogy to some extent.
Yeah, actually, I was going to ask you about that. Like, people have probably thought about how to get superconductivity out of these fluctuations.
Well, there's some work. Igor Mazin has actually, I'm not sure it's a paper. I think it's just notes that he posted on arXiv. There's some discussion of how to match this with, and you're going to kind of need a triplet.
Okay. And is there any candidate material where this would be, can be maybe relevant?
Like to have like the usual picture that we like, that have an altermagnetic phase and critical point. Not that I'm aware of.
Okay.
But for example, as I mentioned, you have these rare titanium oxides, right? They're multi-insulators, but if you dope, they're metals now, they're not superconductors. Ruthenium oxide in very thin film was also shown to be a superconductor. But you see, this is very low when the magnetic phase people have been talking about like 500, 400 Kelvin. So we're not there yet, but hopefully something will show up.
Any more?
Since they published this paper in PRX of spins group and all this formalism, I have seen some experimental realizations of this altermagnetism, but all the time with these collinear spin structures. And you told me that if we apply spin orbit coupling, then this collinearity needs breakdown in order to have altermagnetism. Do you know any experimental realization or proposals? Maybe this one, but you show there are also measurements in.
No, so yeah. So what I mean by non-collinearity is that the spin model, the modulation of the spin, is not going to be the same for all spin components, right? But no, I'm not aware of an experiment that has directly seen that. I think in hexagonal systems, this game is a little more interesting, and you could have that, and I can tell you more later. But one thing to keep in mind is that, let's say that I do an ARPS experiment, and I look at k is equals 0. Then these two terms are gone, and I only have spin z, right? So if you could do spin ARPS and look at different polarizations, you'd be able to see how the nodal lines change the character as you go across the equator, for example. But I don't know of an experiment that would have seen that. There are some more indirect effects, which is, for example, how they couple to phonons, which also be a little bit different if you have or if you don't have spin orbit coupling. But no collinear in this sense, right? And again, like if you look at this picture, so this is perfectly collinear. Well, except that now I have these again, this is empty Wycliffe position. So yeah, you don't have an atom there, but the spin density is present there. Okay, so that's what I was trying to mention. Does it answer your question?
How would local probes
Would see that?
like
Yeah.
NMR or something?
Yeah, so here we're out of luck because there are no atoms in these Wyckoff positions. But do I have this? Let's see. I don't know if I have this in my extra slides. Let's see. If I don't, I will explain with words. There are lots of extra slides. No, I don't have it. Okay. Oops, I lost it. So remember I told you about this rare earth titanium oxides, the PNMA perovskites. It turns out that in that case, the non-collider moments are actually the magnetic. So you actually can see directly from neutron scattering. People have seen it.
Okay.
Okay. So yeah, that would be a straightforward way.
Yes.
So you stress that the bipoles in altermagnets they come from different sublattice, right?
The G-right points, yes. Yeah.
So are they different from like the direct points in normal ferromagnetic material or antiferromagnetic?
Like magnetic biopoints?
Yeah.
I think they are, but I would have to. I have to think a little bit more about that. I believe it's a different mechanism, but you know, I'm not an expert on magnetic biopoints to say that with absolute certainty. I'll be happy to discuss more actually if people were interested.
Any last pressing questions before we let the speaker take him to lunch? No? Okay, so
Thank you.